Let's talk about scatter plots, associations, and correlation. First, let's define what a scatter plot is. A scatter plot is a bivariate visualization of data where both variables are quantitative, meaning we have two variables, an x and a y, and they're both quantitative variables. Association is when one variable tells you something about another, as in the variables are not independent. Correlation is a very specific kind of association, which is only between two quantitative variables. So remember, a correlation is a specific kind of association only between two quantitative variables. Things can have an association but not a correlation, as in something like what test you take might be correlated with the grade. Maybe a professor has version A and version B of the test, and maybe version B has higher grades on average than version A. Now, this would not be a correlation, this would be an association. But maybe we compare things like how long you study for a test in hours and your grade on the test. And now we have two quantitative variables, your grade being the y variable of interest, and the hours you study. And this would be a correlation and an association because it's a special type of association. But over here, the type of test you took, version A or B, and also the grade would only be an association. This is both correlation and an association because a correlation is a special kind of association between two quantitative variables. So far, we've covered a lot of different graphics. If you remember, we did mosaic plots. A mosaic plot is between two categorical variables. And so you could also look at the association between passing and failing and if people take certain tests. Once again, this is an association, but not a correlation because version A and version B can pass and fail. If you notice more people pass taking version B, this is an association between the two variables, but it is categorical, making a mosaic plot. Also, we could display it with a contingency table. Additionally, side-by-side box plots, which we saw just a second ago, would be a quantitative y variable of interest, so the quantitative y, because we're looking at test grades, and the categorical x, which test did you take? So there's many different ways to describe data, and knowing what your variable types is the most important part to understanding how to properly describe them. So let's look at scatter plots. Scatter plots, once again, are the visualization of two quantitative variables. You could have something like GPA and let's say salary. Maybe we were trying to explain people's GPA in school and the salary they get, and we might see some sort of mostly linear relationship, but it might level off, and maybe some weird outliers, like somebody who had a lower GPA who got a really high salary. So there can be unusual things in scatter plots, but once again, the key thing to know about scatter plots is scatter plots are the visualization of a bivariate quantitative relationship, and there we see two quantitative variables and the scatter plot visualizing it. When we talk about scatter plots, there's four things to talk about: the strength, direction, form, and unusual features. It's just the way I like to memorize it: strength, direction, form, unusual features. You can start in any direction you want on these because the easiest one to talk about is going to be direction. Direction is simply, does it go down or does it go up? So we have things that have an upward direction or a downward direction, and that is simply the direction of the scatter plot. So when we do this, sometimes there are things that don't follow a clear direction, like this one right here goes up and down. So you might say it starts out going up and then it starts going down. It doesn't have one clear direction. Other ones go up pretty easily to see, and you just look, does it generally go up? Does it generally go down? In addition to direction, there's also the form. The form is either going to be one of two things. Is it a line or is it not a line? And by a line, we mean, does a line generally go through the data? Now, you can fit a line to any data. I've had students look at data like this, and then I ask them if it has a linear relationship because we fit a line to the data like that, and they say, well, you fit a line, it has a linear relationship. Well, we want to know if the line is a good fit for the data. And if you look, the data has more of a parabolic shape, so we would say it has a non-linear shape. It has a non-linear shape to it. You could say parabolic, but it's either a line or not a line. So when you look at this right here, this is somewhat linear with evidence of nonlinearity at the start, and this is very nonlinear, a parabolic relationship. Fitting the line, and if it mostly goes around the usual form, you're good, but you notice the second one is very bad, so the second one, not really a linear form. Strength is usually the hard one for people to understand, but What is strength? It is how tight the points are around the form. Strength is how tight the points are around the form. So if you have a parabolic relationship like this versus a linear relationship like this, which of these is stronger? The parabolic or the linear? The answer is the parabolic, because around the parabola, the points are tighter. A linear relationship has more spread out points. You can make an even stronger parabolic relationship if you draw the points really tight around a parabola, then they follow the form. So remember, strength is how tight the points are around the form, and the top graphic I just drew right there is a super strong parabolic relationship. So is this one right here. This is a really strong sort of polynomial higher order degree one, and this is a strong linear relationship because the points would be tight around a line. Now, we do have things that have a very weak or non-existent relationship, and they usually look like a big circle right there. And this would be where there's really no relationship, nothing going on with the data, and we can't really analyze it well, and it looks kind of random. So with this, remember, strength is how tight the points are around the form. This is a weak, non-existent relationship and really doesn't have a strong form to it, even though we drew a line. It's just kind of a random, non-existent relationship. So we've covered strength, direction, form, but we haven't covered unusual features. Unusual features are going to be things that are outliers that go against the trend in the data. You can have a univariate outlier, but this right here is a bivariate outlier. As in, somebody could weigh 190 pounds, and that wouldn't be that unusual. They might be at that point like 6'2", that'd be 74 inches right here, and weigh 190, and that's not unusual. But what is unusual is to weigh 190 and be 5'2". And unusual doesn't mean bad, it just means you're away from the centrality of the data. If you draw ellipses around this right here, going outward, you can actually break into the mathematics on this with eigenvectors and figure out the eigenspace and figure out just how unusual this is in terms of extremeness. And if you notice, there's a tighter dimensionality in the direction here. We'll highlight that. Direction going this way is tighter versus the direction in the other one, which follows the relationship. So things that are extremely far away from the form are things that would be outliers. So a good way to check this is to draw the line and then look to see what would be away from a linear relationship. So the most unusual point besides that might be something like this right here, this right here. Nothing is too unusual except for that point. The more usual ones would be ones right around the line, and it'd be these right here that follow the linear pattern and are close to sort of the density ellipse at the center. That's probably the most usual common person because they're like at the mean of the data set. So unusual would mean things that are far away from the bivariate trend, and the bivariate trend right here is a line. So an unusual feature is outliers, things that do not follow the bivariate trend. How about other unusual features? Well, if you notice, this data set kind of has two clusters, a cluster here and a cluster here. Fitting the linear relationship would create an average of these and not really do a good job of explaining the data. So we can split this apart into two separate data sets, and from there add two separate lines to it. And this would do a much better job of explaining what's going on right here with two separate lines to the data. And this is where we get into an important idea of that we have a y variable of interest, and the x variables are our explanatory variables. So the y variable is sometimes called the response because it's what you want to talk about. You're going to ask people about it, it's going to be the response. And the x variables are your explanatory variables. They are going to predict why something occurs. I like to call x's explanatories. Some people in math call them the independent variables, and some people call y the dependent. I don't like that terminology. Y is what we want to understand. Why is this happening? Let's talk about it and give a response. X is the explanatory, which explains why something is happening. To do these graphs in JUMP, we use analyze fit y by x. Notice how we have the x right here and the y right here, and we simply put it into the platform and click OK. From here, we get scatter plots. But there's a special kind of scatter plot called a time plot. A time plot simply has time on the x-axis. So an important note to take right now, time plots are special case scatter plots with time on the x-axis. And you can do things like add a smoothing trend to these, where you can see over time generally what's going on, the nonlinear relationship. We can also do a moving average right here to average out points and kind of smooth that out also. We have advanced courses like time series and statistical process control, which go into these topics into greater detail if you're interested in taking them. But here's an important review question. The graphic on the left is a what? The graphic on the right is a what? See if you can answer these and know what they are. Let's go over that. Well, the graphic on the left is a histogram. The histogram is a univariate visualization of quantitative data. The graphic on the right is a scatter plot, and more specifically, a time plot. The histogram shows that the Kentucky Derby times have a right skew to them, which is going to inflate the mean higher than the median right there, which is the center. We see over time that times have leveled off in the scatter plot, also a time plot, and they've kind of leveled off after about 1985 or even maybe 1967. There really hasn't been a much difference in the Kentucky Derby times. Remember, scatter plots show you the strength, right above here, strength, direction, so it's mostly downward, form, and unusual features. The histogram shows you the shape. From there, we decide the center and the spread. So big differences here between the histogram, where we look at shape, center, spread, and the scatter plot, where we look at strength, direction, form, unusual features to talk about these concepts. So what is this idea of correlation? We talked about it at the start, but how do we find it? Well, correlation is a measurement of the strength between two quantitative variables, which ranges between -1 and +1, where both of these are equally as strong. And the weakest relationship is when you get a correlation of 0. That is the weakest relationship right there. So here is how it's found. Now, doing this by hand is not that fun, but I want to point something out, that correlation can use z-scores, which means correlation like z-scores are unitless. There's no, this much value of correlation because it's calculated from z-scores, so it's a standardized metric to talk about. That means, and this is good help for your questions on your quizzes, if you were to change the units you measure something in from miles per hour to kilometers, it's not going to make a stronger or weaker correlation just because you're changing it from Fahrenheit to Celsius for temperature. The temperature would still be correlated with, I guess the amount of snow we get. If we look at the amount of snow on the ground and the temperature, you'll notice that the colder it gets, the more snow we get. So there's a negative correlation. As temperature goes down, amount of snow goes up. And you would not change that by measuring amount of snow in inches or feet. And you wouldn't change it by measuring the temperature in Fahrenheit or Celsius, because when you do these calculations, all of this data is turned into z-scores anyway. So with this, that is the important thing to know, that correlation, at least by the way we calculate it, is a standardized metric, and so the units of the problem won't make a difference. Here we are with what correlation can look like if it's pretty moderately strong. Now that's just subjective words, but I like to say something is moderate around 0.5, and I like to say it's strong around 0.75, and I like to say it's weak around 0.25, and non-existent around 0. That's non-existent. And then at 1, it's perfect. And just so it's clear, 0.75 is strong. So since I said this is moderately strong, what do you think the correlation is? Remember, I said moderately strong. You might say, how did I know that? Well, 1, I've looked at a lot of these, and 2, the answer is on the next slide. So 0.64, if you notice, is in the range between what I call moderate and strong. These words are not things that you have to say. Someone might have a different cutoff for what strong is, or moderate, or weak. But if you think making a gradient from 0 to 1, and I do want to mention this, the sign doesn't matter because sign would only indicate direction. So even if you put negatives in front of these, negative 0.25 is still weak, negative 1 is still perfect, just perfect negative. All you would be doing is taking these points and making them go down. I do want to point this out because if the direction changes, the tightness around the form would not change. If you look at how tight those points are, even if I make them go down, they still have the same tightness around the line, which is the way we measure strength. So it's different topics to say it's negative, because negative is going to be the direction of the relationship, where strength is the tightness of the points around the relationship, around the form. What does this mean in terms of strength right here? Once again, we just said it, that strength right there, the closer it is to -1 or 1, the stronger it is. So we got some other good questions here. What does the sign of the correlation coefficient indicate? And this is the sign of R, where R is contained between -1 and 1. And the sign of it is going to indicate to us whether it is a positive or negative direction. Whether the points go up or whether the points go down would be positive or negative. And whether they have next to no relationship could be 0 right there. What are the possible values of correlation? Anything between -1 and 1 inclusive of these values. So anything between -1 and 1 inclusive of these values. What if a relationship is strong, but it's not linear? The best example of this, and we put this on the test all the time, is a parabola. Is this strong, yes or no? Yes. Because if you draw a parabola, the points are tight around it. But when we measure correlation, correlation only measures linear strength. I can't say that enough. The correlation value R only measures linear strength, which means the line would have a correlation of 0. So the linear relationship there is non-existent. And so a strong relationship can have a non-linear relationship, and thus the linear relationship comes back as a non-existent. Now we've got our conditions. To do these ideas, we need to make sure we're doing them properly. Just like with the normal curve, we need to make sure our data is normal. Well, scatter plots, we said, are 2 quantitative variables. So we have here a quantitative x and a quantitative y. So 2 quantitative variables. I like to call this condition QQ. So QQ, 2 quantitative variables. Straight enough. Straight enough means it kind of follows a straight line, and then no outliers is what it says it is. And I had my students chant QQ straight enough, no outliers. So how would you check this? Let's look at some data. QQ, is it 2 quantitative variables? Well, first off, it's a scatter plot, so yes. Second, baking temperature. Yeah, that's quantitative. How much do we bake it at? And it's math. You've got numbers right there. And then how much do you like the taste? Well, that can be math also, because a taste rating of 5 is higher than a taste rating of 4, so that's quantitative. So we have 2 quantitative variables. Straight enough. That means if I draw through the data in the proper form, not straight enough. No outliers. This one really doesn't have outliers because these don't really go against the bivariate trend. It's just that the form of this is not linear. We did see some earlier ones that were really great. We'll go back to an earlier one that would pass QQ straight enough, no outliers. This one right here that we saw would be a good example of 2 quantitative variables, and let's show it. We would say, if we were asked about this, that central pressure in MB is going to be quantitative. It's a real number. Max wind speed in whatever that is also quantitative. And is it straight enough? Well, a straight line looks to go through the relationship. And no outliers, you might say there's a tiny bit of concern with those because they're the furthest away from the relationship. There's no extreme outliers. Sometimes you look for things that are very unusual. And we did see one like that also with this graphic. This is 2 quantitative variables. Height is quantitative, weight is quantitative, so we're good on that, QQ. Is it straight enough? It is straight enough. The line goes through the data pretty well. The line fits the data. And then this does have more of an extreme of an outlier right there. So we might say there's a bit of an issue with the one extreme point of an individual who is 71 inches tall and weighs about 280 pounds. It's always good to mention your outliers in your write-ups to say like, well, there does seem to be one pretty unusual point. So I am concerned about the no outlier condition. So we have the conditions QQ, 2 quantitative variables, straight enough, a straight line approximates the relationship, and no outliers. We don't want to see outliers in the data. You might say, why don't we want to see outliers? Well, we could have a weak correlation like this. This would have a correlation equal to 0. But one outlier over here could drastically change it, and you'd be shocked. Something like, I put the dot in the wrong spot. Can't have a correlation outside of 1, so don't do that right there. Could change it to a ridiculously strong correlation. How about this right here? Sketch of an outlier making a strong correlation look weak. So you could have a strong correlation here between a few points like that. and that would be a correlation of 1 basically. And then you would have 1 point over here in the extreme, and that can actually make it a correlation of 0 when you add in that extra point. Sketch of a outlier making a positive correlation look negative. So we actually kind of just did that, or we could do it more in the extreme. We could take this outlier point and bring it down here. So now the relationship would be like this, and with the outlier, it's going to cause a relationship like that right there. So if you notice, outliers can do anything. We can make a negative relationship look positive. We can make a positive relationship look negative, a strong relation weak, a weak relationship strong. And I want to say this so many times. I love this because when we give test questions, I tell my students anything is possible when it comes to outliers and correlation. Be careful. Outliers don't impact the median. So if you're thinking outliers can do anything, they don't impact the median. That's one of the few things they don't impact. But outliers can impact the correlation value, the R-squared value, if we talk about that, the mean, all these different things right here, the standard deviation are impacted by outliers. That's why when we do this analysis, we don't want there to be extreme outliers, or they'll be the ones dictating the relationship. So a huge warning here, correlation is not causation. It doesn't matter how close the value of correlation is to 1 or -1. You can have a perfect correlation of 1 and not show causation. Think about it. 2 points. Any 2 points, as long as they're not a flat 2 points, would have a correlation of 1 or -1 if they went downwards, because 2 points are connected by a line. So this would not be proof of causation. And a lot of people use this the wrong way because they think things like, oh, shark attacks are going up and ice cream sales are going up. So there's got to be some sort of causation that maybe when people sell ice cream, it causes sharks to attack. Well, not exactly. This is probably due to what we call a lurking variable. A lurking variable is a variable outside of x and y, where when you have this lurking variable, it may look like x and y are related. But there's this other variable in the middle here, which would be summertime. And summertime is the real reason, or we would think, behind ice cream and sharks. More shark attacks, probably due to summertime. More ice cream sales, probably due to summertime. But because of this lurking variable being related to these, it almost seems as these two variables are related. So it's very hard to tell sometimes. We sometimes call this a z variable. It's outside of the xy relationship. So if you say maybe ice cream sales explains shark attacks, actually it may be to a variable outside of it lurking outside the model. So be very, very, very careful right here. No matter how high we make the r squared or the r, which is r squared is just r squared. If we have correlation of negative 0.99, it doesn't matter. It's not going to show causation. How about with a correlation matrix right here? A correlation matrix shows you all the combinations of the different variables. You really got right here variable 1, and it does repeat on the other side with variable 2. And then you want to look at the combinations of the variables to see what is the correlation between body fat and weight. And the correlation between those two variables is 0.6132. What is the strongest correlation in this matrix? Well, the strongest correlation would be closest to -1 or 1. And it looks to me, if I get this right, there's the strongest. JMP also does color code them. Now you might be wondering why I don't say negative or 1 right here, because that is just between the same variable. So usually we don't pick these on the diagonal because thigh measurements are correlated with thigh measurements at 100, or totally 1-to-1 correlation because it's the same data we're talking about right there. But the strongest correlation is going to be the one that is closest to 1 or -1. How about the weakest? The weakest correlation will be closest to 0. And with this right here, it looks to me, and I'll double check my work right here. I think I see it. I'll do a quick double check. It looks like that right there. That's the closest to 0. And yes, this matrix is symmetric, which means if you look at either side above or below this, it is going to be the same values. And yes, -0.01 is going to be the weakest correlation. We can do all these things in JMP right here by going in and selecting analyze multivariate methods, multivariate. Really good stuff right there. And last but not least, we do come back to statistical significance. Anytime you hear statistical significance, immediately think p-value. And specifically, p-value less than 0.05 is that's when something is statistically significant. Now, we talked about null hypothesis in the last chapter. We can use it again here. The null hypothesis now is no correlation. The alternative, which we're going to look for evidence for, is evidence of correlation. Now, if we see a high p-value, then what we saw was likely to see given no correlation. And think about what is likely to see if there's no correlation. Something likely to see given no correlation would be no correlation. It'd look probably like this. That's when there's no correlation, and this is what's likely to see, and that would be a high p-value. Now, what would be unlikely to see if there's no correlation, which would be something where there's correlation. This would be an unlikely thing to see and a low p-value. So p-values just tell us if what we saw was likely to see given the null is true. If the null is true and there's no correlation, I should see something where there's no correlation. And this is a likely thing to see, high p-value. If the null is false, then I saw something unlikely, or I should see something unlikely, and I should see what looks like evidence of correlation, because I'll reject the null and say I have evidence of correlation. So let's look at some of the examples of this, and here's our data. Now, first off, the correlation value in this data set is 0.6232, and that's because we're looking at strength and thickness. And so the bivariate combination of these two variables right here leads to this plot in the scatter plot matrix and up here in the correlations matrix. You can also see the value of correlation down below in the pairwise correlations. And then last but not least, more importantly, the p-value. Now notice p-value is less than 0.05. That means we reject the null that there is no correlation and we have evidence there is correlation. Very important to know how to look at this output right here and know that the p-value is statistically significant because it's less than 0.05. And additionally, we see evidence of correlation because we're doing a test on the correlation value. We're asking, is the correlation statistically significant? Is what we're seeing here likely or unlikely to occur given there is no correlation? Basically, we're saying, I think there is correlation. I think we have good evidence. And with that, we're done with correlation. Make sure to ask any questions and keep up the good work.